So today we are going to start something which is neither a data structure nor an algorithm. Okay, rather it is a kind of technique. Okay, it is just a technique, and this technique is very simple, yet it is very profound. Okay, so what I mean by simplicity is that it is very easy to to reason, to put forward a logic whether this approach is applicable in this problem or not. Okay, but it is very powerful because it significantly reduces time complexities from something like n log n to n. Okay, so that being said, this is an extremely important approach, and this is also called as, what we are going to learn today is called as two pointers. So this pointer is not like the pointer type of any language which actually stores address of a variable. This is not that, it is different. Okay, cool. So let us start. Let me give you a question to start. So if I have given you an array of size n, and I give you another integer k, okay, I ask you to check if there are two indices I and j such that I not equals to j and array I plus array j is equal to k. I ask you for this. So read this properly. Basically the intent is that an array has been given and you are supposed to tell me whether there are two elements in this array located at different indices, obviously, because I don't want you to pick the same element at same index twice. So whether or not there are two elements located at different indices such that their sum is equal to given thing or not. So if it is so, then you have to return true, and otherwise you have to return false. So tell me, what is the way to solve it? So the brute force solution would say that you would want to consider all the pairs. So while considering all the pairs, you will be having an outer for loop and an inner for loop, right? So the complexity of that would be order n square, right? Cool. So the complexity of that approach is order n square time and order 1 space. Okay. Now my question is, can I do better than this? Can I improve it from order n square time? For every number we search this in an unordered map. Okay, cool. That also makes sense. So one of you is saying something like this, that I want to check whether or not there are two elements with sum equal to k. So let's say the array contains 5, 6, 9, 4, minus 1, 10, and you want to check whether or not there are two elements that are having sum, let's say 9. So what you can do is you can simply iterate over this array, and whenever, let's say, you have considered your reference element as array of I, automatically your another element becomes apparent to you, and that is nothing but k minus array of I. So you just need to be able to check whether this k minus array of I is present in the array or not. Okay, now one way to easily do that is to store all the elements in a hash map. Okay, if you store all the elements in a hash map, then you can check the presence of an element in a really simple manner. Okay, you just have to be careful about one particular thing. Let me ask you that. So let's say you have populated the hash map. So in the hash map, you see you have 5, 6, 9, 4, minus 1 and 10. And let's say k is equal to 10. Just listen to the question very carefully. K is equal to 10 and you have started your iteration from here. So if your reference element is 5, then for this particular value of k, what will be your other element? That will also be 5. And now you will check whether this 5 is present or not, right? You will check whether this 5 is present in the map or not. So what will the map say? Will it say present or absent? It will say that it is present, right? So you might end up returning true, but is that right? That is not right. So can you handle this? Guys, can somebody tell me that instead of storing 1 in the value portion of every key, Can I store something else so that my life becomes easy? Count, yes, which is frequency. Does that make sense? Cool. So what I can store is, I can store frequency. So in that case, if let's say there were two occurrences of 5, then I would have seen that 5 comes for 2 times. So if such kind of scenario arises where array I and k minus array I are same, then the frequency of this thing must be greater than 1 for the answer to be true. And if the frequency is 1, then answer will not be true for this particular array I. In that case, I will move on to the array I plus 1. So in the map, if you have element along with its frequency, then your job will become very, very easy. This was one really simple and really intuitive fix for that. Let's say you are assuming a map like unordered map that supports a lookup and insert and everything of order 1 on an average, right? So what would be the, first tell me, what would be the time complexity of this? Order of n, right? Order of n, because you are iterating over all the elements, and whenever you are at an element, you are just doing a check in map, which is order 1. Okay, so order n is your time, and how much is space? So amount of extra space will be equal to the amount of entries in the hash map, right? Now entries in the hash map, how do I decide how many entries in the hash map will be there? Can somebody tell me that? Yeah, it will be number of unique values. Yes, great. Because if let's say all the elements were 5, 5, 5, 5, 5, 5 each, then 5 along with n would have been the only entry in the map. But in the worst case, what can be the total number of distinct values? In the worst case, it can be n. So I always speak about complexity in the worst case. So in the worst case, it will be order of n. So when I tried to decrease this increased. Okay, cool. So let us try to figure out a middle way, something in between this and this, where I am able to reduce the time complexity from n squared to something else, and that something else can be greater than n, but I don't use any extra space for that. So can somebody think of an approach like that? Sort the array and then do binary search. Excellent. So, yeah, so that makes a lot of sense. So what you can do is you can just simply sort this array. So if you sort this array, you will get minus 1, then 4, 5, 5, 6, 9 and 10. Okay, now whenever you are at an element, your counterpart is k minus this element, which is 11. So you would check whether 11 is present or not. So in which portion of array will you check whether 11 is present or not? Will you check in the entire array, or will you just check in this much portion? You will just check from I plus 1 to n minus 1, right? So you will check whether it is present in this portion or not. And now this is sorted. So can I use binary search to check whether this thing is present in this region or not? The answer is yes, binary search can be used. Okay. Now if I found it, I will return my answer, and if I did not find it, then I will move on to the next element, and then again I will do my job. Then I will move to the next element, and then again I will do my job, right? But you understand this clearly, right? That whenever you are fixing this as your reference element, then k minus reference element is being searched in this much part and not that. Why? Because you might end up considering the same element again. Okay, this is the reason behind this. What will be the time complexity of this approach? And log n. So let's talk about the time complexity of this approach. So when you have fixed your a of 0 as your reference element, at that point of time you are searching for k minus a of 0 in this much portion. Can you tell me how much time will this search process take? Log of n minus 1, to be very, very exact, right? So the first step will be of time complexity log n minus 1. Now when you are here, then you will search from here to here. What will be time complexity of this? You should have said log n minus 2, because I picked this second element from here, so I've got n minus 2 elements left. So log n minus 2. I'm not sure why this is not clear. This is very easy. Similarly, for next element it will be log n minus 3, and so on till log 1. If I add this expression, what will I get? What will I get if I add this log n minus 1 plus log n minus 2? What is the value of log m plus log n? Log m plus log n is log of m into n, right? So this entire thing will be added, then these things will be multiplied. So it is multiplication from 1 to 2 till n minus 1. So continuous multiplication from 1 to n minus 1 is n minus 1 factorial. I can roughly write it like n factorial. So it will be log of almost n factorial. And what is the highest power of n in n factorial? What is the highest power of n? That is n. So it will be around log of n raised to power n plus some other terms. Those other terms can be ignored in front of this. So it will be n into log n. So n log n time is consumed in this process also. And there is one more step where n log n time was consumed. Can somebody speak of that step? Sorting. Yeah. So n log n in sorting and n log n here. So overall it is n log n. In this entire process, did I require any extra space? Did I require any extra space? No, I did not require any extra space. Okay. Cool. So this was order n log n. Cool. Yeah. Now my question from you is that once you have been given this original problem where this array was originally unsorted, the point is of, see, if you look at the different approaches out there, 3 approaches we have seen, right? The most important thing that we are doing is search, isn't it? Yes, no. The most important thing that we are doing across all the approaches is search. In the first approach, it was a naive search, which was a linear search that was order n square. For every element, you linearly search for its counterpart, right? In the other approach, it was a map-based search where map makes it easy for you to search. You don't have to worry a lot. In the third approach, it was binary search because you actually sorted it. Okay. Now, I would want you to stop here and see one thing very clearly. If I tell you that this input array is already sorted, so this is already sorted. Now, how much time can you take to solve this problem? So, if it is already sorted, then let's say if you are using this approach of binary search, still you will take n log n time, yes or no? Right? Still you will take n log n time because the process itself takes n log n time. This is what I wrote, right? So think of it in this way that, hey, if it is already sorted, can I use my brain in a bit different manner and then try to solve it? So some of you talked about 2-pointer approach. Okay, so let us understand that very, very conceptually. Okay. So guys, this is the most important example. I will give you enough time over here, but in the next questions we'll be fast. Okay, so try to understand this thing extremely clearly. So the point is that the array is sorted. Okay, the array is sorted. So array will contain something like A0, A1, A2, A3, A4, A5, A6, A7. Let's say there are 8 elements like this and the array is sorted. Okay, this is sorted. So think of it in this way. 2-pointer approach means that you basically use 2 variables. And now 2-pointer is not the generic name. The generic name should be using k pointers. Sometimes you might want to use 3 pointers, sometimes 4 pointers and so on. Okay, so I'm just trying to show you one thing over here. Just think of it in this way that I am focusing my attention on this variable and this variable. Okay, and the sum that I want to make is k. Let's say I saw that A0 plus A7 is equal to k. What should I do over here? You're trying to solve the original problem and you saw that A0 plus A7 is equal to k. What will you do? You will just return true and that's it, game over, right? Cool. So if I compare A0 plus A7 against k, then there can be this possibility and there can be some other possibilities also in terms of their relationship. Can you tell me how many more possibilities can be there in terms of their relationship? 2 more possibilities, right? And what is that? First possibility can be that this particular thing happens to be smaller than k, and then next one can be when this particular thing happens to be greater than k. Okay, so this is very easy. This is my exit. I immediately exit here. Now let us examine this. Let us see if this happened. So I found that this thing plus this thing was greater than the value that I wanted to make. Okay, so tell me one thing. If you are trying to create a pair, okay, and in that pair you are rigid about the fact that you will take this element. You are rigid about it, that hey, I'll take this element for sure. Okay, can you tell me what should be your second element so that the sum of these is minimal possible? It should simply be A0, right? Because A0 is the smallest such element. Okay, so if you are rigid about this, then A0 plus A7 is the minimum most value that you can attain. Okay, now if this value, which is this, okay, if this value, let's come to this case, sorry, let's come to third case. So if this value itself happened to be greater than k, okay, so if this sum happened to be greater than k, can I say that A7 plus A1 or A2 or A3, whatever you take, that would also be greater than k? Can I say it? Yeah, I can say it. And why I can say that? I can say that because it is sorted in ascending order. So if you fix this and if you increase this, because if you don't take this, you take something to the right of it, and all of them are greater. So if this was smaller than k, sorry, if this was greater than k, then these things would be even greater than k. So can I simply say that, hey, this element is going to be useless element for everything from here till here, because this does not have a potential to make that pair. Yeah, so this is the most important thing about it. So what you can do is you can completely just discard this element, and discarding this element means that you will move this pointer to here. Okay, what is the physical significance of these pointers? So if I name them, if I name these pointers, let's say I say it I and I say it J. Okay, then the physical significance of these pointers are that portion from I to J is my portion of interest. Okay, so everything that is towards the right side of J was detected as useless, so I will never ever go to that. And everything in the left of I was also detected as useless, so I will never ever go to that. Now let us move ahead from here. Yeah, now let's say a situation happened where you are comparing A0 and A6, and you found that A0 and A6 was smaller than k. Okay, A0 and A6 was smaller than k. Now tell me one thing. Here I asked you to be rigid about the element at this end. In this case, I am just asking you to be rigid about the element at this end, which is, let's say, A0. So let's say I ask you that, hey, you be rigid about taking A0 for sure. Okay, and then the other element that you will take, can you tell me what should be the other element such that A0 plus that other element is maximum possible? What should it be? It should simply be A6. A7 is not the right answer. I repeat again, A7 was useless. You do not take useless elements. That is the reason I spoke that line, right? You never consider useless elements. So please do not consider it again. Okay. So here you would have said that A6 is such element with which A0 plus A6 will be maximum possible, right? Now if this thing itself is smaller than k, can I say that A0 plus anything which is in the left side of A6 will be even smaller than k? Got it? So this being the reason, what will I do? This being the reason, I can easily say that, hey, this A0 is basically useless for all these. This does not have capability to pair up with any of the elements in this part and create a sum which is equal to k. Right? So in this case, what will I do? I will move this pointer. Yeah. So did I check out for all these three cases? So when you are comparing, if they are equal, simply return true because you got a pair with a given sum, right? If the sum is greater, let's say here the sum is greater, what does it mean? It means that this thing summed up with this thing is giving me a value which is greater than k. So this thing summed up with any other thing will give me a value which will be even greater than k. So this thing is useless. So whenever you see that this thing is useless, what do you do? What do you do with j? When you find that this thing is useless, you decrement j by doing j minus minus. Very good. But if you find something like this, that the sum happens to be smaller than k. If the sum happens to be smaller than k, then you think about this. When it was greater than k, then you think about this. When it is smaller than k, then you think about this. Then you think that, hey, if this thing with this is making a sum which is smaller than k, then this thing with all these will make a sum which will be even smaller than k. So in that case, you will regard this thing as useless and move this by doing I plus plus. So this is the major philosophy behind two pointers. So the pointers that you are using, no matter how many pointers you are using, okay, you should understand the physical significance of them. The physical significance here is that everything in the left of I is useless. Why they are useless? I had spoken the reason behind that, right? Similarly, everything towards the right side of j is useless. So I will never ever touch them. So see, how is it making things more efficient for me is that the elements that are getting discarded, be it in this end or be it in this end, are never getting considered again. What I mean by that is, so let's say the pointers moved and moved and moved and they came here, okay? So now with A3, A4 is the only pair that you can make, and let's say there were certain other elements in between. I'm just writing them P, Q. So this is your area of interest. So for A3, you will never ever consider these things and these things again. Okay, so this was something that you were doing in the naive approach, and you were also doing in something like binary search, where for A0, if you considered A1, A2, A3, A4, A5, then for A1 also you are considering these things again. Okay, but in this case that is not happening. You are getting rid of elements from this end also, and you are getting rid of elements from that end also. The time complexity will be order n. And what will be the termination condition? Till when would you want to just keep on running the loop? Yeah, so as long as I and j are such that I is towards the left part of j, you will keep moving. Okay, you will keep running your algorithm. And okay, what is the most important requirement for this approach to work? The array should be sorted, because every logic and reason that I gave, it revolved around the sorting nature. So if this thing is not present, then this approach will mostly not work. Okay, so okay, let me not make things too generic or something that you can easily mug up, because it is not necessary that for k pointer approach to be applicable, the array has to be sorted. It is not necessary. Another thing, it is not necessary that the pointers I and j always have to start from the borders. It is also not necessary. Are you getting my point? This is not at all necessary. Here, so you have to think of multiple things. First thing is that what is the physical significance of your pointers? Second thing, what is their initial positions? So here the initial position was at borders, but it is not necessary that they will always be at borders. Okay, that you have to think, where should it be? Okay, so these two are the most important things, and the third and last most important thing is how to change them. So behind change, there is the logic that you change them once you are clear that what is useless and what is useful. Based on that, you move them accordingly. So this is the way you get your job done, and I think writing the code for this would be very easy. And why is the time complexity of this approach equal to order n? If your interviewer asks you, what will you say? Every element is being touched just one time. No element is being touched two times. In other words, in every iteration, I am either moving 1 unit right or 1 unit left. So after n iterations, I'll meet somewhere and my job will be done. Cool. So guys, I made some important points. So please keep that in your mind. You have to decide how to initially orient your pointers. Okay. You have to decide how to change them. You have to decide everything about it. Okay. You cannot just mug this thing up that I'll keep them here, move them like this and move it like this. No, that is not going to help you out at all. Okay. Cool. So how will the code of this look like? I will have a pointer I initialized to 0, j initialized to -1, and while I smaller than j, I'll have those three conditions and my game is done. So if ai plus aj is equals to k, return true, else if ai plus aj happens to be smaller than k. If it happens to be smaller than k, what will you do? Yeah, if this sum is smaller than k, what will you do? Which pointer will you change? You will change I, right? Because of the same reason, because if the sum of ai and aj happens to be smaller, then this element happens to be useless, because this along with all of these will make an even lower sum. So I'll change I. So I'll do I plus plus. Otherwise, what will you do? You will do j minus minus. Okay, and in the last you can write return false. So return false means that you have not been able to detect any pair, so you need to return false over here. Cool. So with this particular approach, you can answer true or false in just order n time.